Okay, a lot of what we do at the beginning is review. You're not expected to just launch right into stuff that you've never seen before. So this is going to be a review. We're trying to do two sections today. One of them is about real numbers and the properties of real numbers, and the other one is about algebraic expressions, and remind ourselves what we mean about that. The objectives normally come, I just take them right from the SOLs, just because, they come in and they look at our stuff, they want to see that. So it's okay. There's only one SOL that's addressed in the things that we're doing today, and that's the first one. The other two I just wrote review. They're really not covered by one of the SOLs. Holy cow. I'm on the wrong, it's okay. Okay, so real numbers, right? We're talking about properties of real numbers. So first we have to talk about what is a real number. Well, real numbers are made up of a bunch of subsets of numbers. Basically, real numbers, there's two kinds of real numbers. There's what we call rational numbers, and there's irrational numbers. Before we get to rational numbers, we're going to talk about all the subsets that fall underneath that. Yes? Yes. So the first set of numbers always starts with the natural numbers. The natural numbers are 1, 2, 3, comma, dot, 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 goes on forever. Those are also called counting numbers. If you add a 0 to that, you get what's called the whole numbers. So 0, 1, 2, 3, comma, dot, 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 go on forever, always positive. That would be a whole number. Those are nice to know, not really going to be that useful. These next two, I'll tell you where integers and rational numbers are important, is that when you take the SAT, they expect you know what these words mean. When they ask a math question that says, find the integers that, they think that you know what they mean by integer. And if you're sitting there scratching your head saying, I don't even know what that word means, then it's going to be harder. Right? So you definitely want to know. Integer means it's the whole numbers, 0, 1, 2, 3, comma, dot, 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 goes on forever. But then also the negative whole numbers. So if you go -1, -2, -3, forever, that would be integers. So you definitely want to know what an integer is, because it'll come up and they're not trying to trick you. They're just trying to think they're using a math word that you would understand by that point. And the other word that you really have to know what it is a rational number. Right? A rational number is a fraction, or something that could be written as a fraction. So when you see the word rational, in your mind you're thinking fraction. And I can tell you that even up through calculus, when we say, what's a rational number, we still get kids scratching their head. And it is supposed to be something that we kind of understand. I mean, just think, rational is like a ratio. A ratio is like 1 to 3, 2 to 5. It's a fraction. So when you see rational numbers, you think fractions. Okay, so let's see. In this list of the examples of rational numbers, you see 2/3 and 5/4. Clearly those are fractions. Why would they be including in that list 1 and 2? Yeah. Yeah, because a rational number is any number that you could write as a fraction. And we could stick those numbers over 1 and they would be as fractions. So we're definitely going to say this is like 1/1 and 2/1. That makes those rational numbers. How about 6.1 right here? 6.1, well, we know what the 0.1 means, don't we? What does the 0.1 mean? Say again? It's a tenth, right? It is 6 1/10, which is like 61 tenths. So that would be a rational number. And I think they've made a little minor mistake on their slide here. This is just copied from your textbook, all right? But this 0.2 .222, I'm assuming that they mean to be like, that means .222, the 2 goes on forever. So it actually has a pattern to it that repeats. So basically, rational numbers can be written as fractions. Right? And that includes decimals that terminate like 6.1 or repeat like 0.2 repeating. Okay. That's rational numbers. So what does that leave for irrational number? Irrational meaning not rational. That would leave us decimals that don't terminate and don't repeat. Okay, that's what an irrational number is. And they've given us 2 examples here. Decimals don't terminate or repeat. Okay, so you can see the 2 numbers that are there. What is that one? It's a pi, right? What is pi? Yeah, it's a value 3.14156 ... goes on forever. Never terminates, never repeats. That is a special category, right, of an irrational number. But also, if you have like the square root of 2, if you have a square root that cannot be simplified, then that will also be a decimal that doesn't terminate and doesn't repeat. Now, if it's like the square root of 25, well, that can be simplified. That's 5. But a square root of 24, okay, that can't be simplified. So that's irrational. So usually when they're talking about irrational numbers, they're going to either give you like pi or a square root that you can't simplify. It's not the square root of a perfect square. And I'm going to add this thing in here. Just, you know, you got a lot of bright kids in here. Somebody might be interested in this. This is how do you know that the square root of 2 is irrational? I mean, how do you know that kind of thing? And this is a proof. This is a mathematical proof that the square root of 2 must be an irrational number. And yes? Well, I'm not sure that's a proof. This would be an example of a proof, right? And if this is just for one square root, it's not like talking about all the square roots. But this is something you might have had a little bit of proving things in geometry. We don't do much of that anymore in geometry, but if you do any proofs at all, it is in geometry. But here's an example of how you do a mathematical proof. The square root of 2. If we say if we want to prove that that's irrational, let's assume that it's rational and show why that leads to something that can't be true. So we're going to assume that the square root of 2 is a rational number. Okay, again, what does it mean to say that the square root of 2 is a rational number? That it could be written as a fraction, right? Okay, so let's say that that square root of 2 equals a over b. And where we're going to say this a over b is a simplified fraction. Right? There's no common factors. If there was, we're reducing it down so we can write this in terms of the most simple fraction. That's the square root of 2. Okay? So now let's multiply both sides times b. So we've got b times the square root of 2 equals a. Okay, now square both sides. Right? If I square the a, I get a squared. If I square b, I get b squared. What do I get if I square the square root of 2? 2, right? So now I've got 2b squared equals a squared. Okay, if a squared equals 2 times a number, is a squared even or odd? It's got to be even, right? It equals 2 times something, so it's got to be an even number. So if a squared is even, what does that tell you about a? Is a even or odd? It's got to be even. If you square an even number, you get an even number. If you square an odd number, you get an odd number. So that tells us that a is even. Okay, so let me come back here, and I'm going to say the square root of 2 equals 2 times, and I'm going to call this a prime. So a prime is like the whatever the number is divided by 2. We know a is even, so we're dividing it by 2. And now I've got that over b. So I've taken this thing right here, and I've rewritten it where I'm just acknowledging the fact that a, we've said, has to be an even number. Okay, now I've moved the b again. B times the square root of 2 equals 2a prime, and now square both sides. Okay, now I'm going to get 2b squared equals 4 times this a prime squared. Okay, now if I divide both sides by 2, right, there's a 2 there and there's a 4 there, that tells me that b squared equals 2 times this a1 prime, or a prime squared. Okay, what does that tell us about b now? Yes? I can't hear you. What's that? Okay. What do we know about b squared now? Since it equals 2 times something. It's even, right? So now we know that b squared is even. What does that tell us about b? b is even. Okay, but remember, we assumed that the square root of 2 equaled some fraction that was already simplified. But if both a and b are actually even numbers, was that a simplified fraction? No. It wasn't, right? So our assumption that the square root of 2 equaled some simplified fraction a over b is proven to be wrong, which means you cannot write the square root of 2 as a fraction. It's irrational. And you can find proofs that show you like the square root of 3, the square root of 5, and more generally, since we're going to assume that any unsimplified square root must be an irrational number, then you would need a more general proof that shows why it would be true for any of them. It wouldn't be enough just to show it for a few numbers. But that is kind of an example where you assume something and show that leads to a false result, and that means your assumption must have been wrong. Okay. You're not going to be tested on that. I just thought it was an interesting kind of thing to look at when you're talking about rational, irrational. Now, complex numbers. The truth is that the one SOL that we've got that is addressed by this lesson, it actually says we're supposed to know which of the what they call field properties apply to complex numbers. Complex numbers are not the same thing as real numbers. We get to complex numbers later on when we're studying quadratics. But at that point, they don't address properties at all. But the properties are pretty much the same. The things that we're going to study now are really the properties that they're testing you on when we get to the SOLs. So this is the right place to talk about properties. And we'll think of them as being properties of complex numbers. Yeah. You don't have to worry about this. We will get to this later. But that is, if you read the objective really addressed something called complex numbers, not real numbers. Okay. Now, every one of these graphics that you see is just taken right out of your book. Okay. So here's our properties. Some of these, you probably have seen them, you probably know them, but maybe you've forgotten them. But we do use these. Something like, for example, this commutative property. A plus B equals B plus A. 2 plus 3 equals 3 plus 2. Is it true? Right? So what is it telling you? Order isn't important, right? If you're adding two numbers, the order you add them up is not important. The same thing would hold for multiplication. 2 times 3 equals 3 times 2, right? Order is not important. Commutative property holds for addition and multiplication. Would commutative property also hold for subtraction?
No.
Give me an example where it does not work. 3 minus 2 is 1, 2 minus 3 is -1, not equal, right? So this property wouldn't hold for subtraction. It's just for addition and for multiplication, right? So again, commutative property is order. Associative property. A plus B in parentheses plus C equals A plus B plus C in parentheses. What's changed? The order is the same. The parentheses, the grouping, right? So in the associative, if you move the parentheses, it doesn't change the result. So you might call that grouping. Okay. And that would hold for multiplication also. Identity. What number can you add to anything and get the same number back again? 0. So 0 is called the additive identity element. Okay. What number can you multiply times anything and get the same thing back again? 1. So 1 is the multiplicative identity element. Okay. And the inverse, you know, if you have a number, if you want to get back to 0, you would add its opposite. So what do I add to 4 to get 0? -4, right? If I have -3, what do I add to get 0? 3, right? If you add the opposite, then you get back to 0, which is the identity element for addition. What do you multiply? What would I multiply if I had like, let's say, 4? What do I multiply times 4 to get back to the multiplicative identity element of 1? Divided by 4 or multiply by 1/4, right? What if I had a fraction of 1/3? What would I multiply by to get 1? 3. What if I had 4/5? What would I multiply by? Okay, you would multiply by, that is called the multiplicative inverse, but it also has another word. Do you remember what that word is? I just said inverse. Starts with an R. The reciprocal, right? If you multiply any number by its reciprocal, by its flip, then you should get 1. Okay. All right, now distributive like is a combination of multiplying and addition, so it kind of falls in the middle of those two. We do a pretty good job of recognizing distributive property when we see it. And then there's one other property which is here, which I've never seen tested, but the closure property just says if I add two real numbers, I get a real number, right? It doesn't become some other kind of number. If I multiply two numbers, I get a real number. It doesn't become something different. So do you remember these properties? A little bit, vaguely, right? Ready? Okay, so let's see, what properties are we talking about here? -2/3 times -3/2 equals 1. What's that? Are we done? Isis? Anybody? Yes. This property? You mean the right thing. What's the property called? It's not called the reciprocal property. Say again. Well, it's multiplicative, but what is the property? When you multiply a fraction times its reciprocal and get 1, what property is that? That's inverse, right? Okay, what about this one? What property is it that takes you from the left-hand side to the right-hand side? I mean, you think associative because you see parentheses, but did the grouping really change? Because what's inside the parentheses on both sides? 3 times 4, right? The grouping, it's still the same two numbers, but what's changed? The order has changed. So what property is it? It's commutative property, commutative of multiplication. Yes? No? We ready? Again, these are in your book. They're just copied straight out of your book. Which property are we using here? How many say distributive? Okay, so it looks like we've got the 3 times G and 3 times H, 3G plus 3H, distributive. Okay, this problem you don't have to try. I'm going to show it. Well, you're going to do part of this. This is exactly the kind of problem you get on the SOL. And the SOL has like 50 questions that count. There's one property that deals with properties. There's one question that deals with properties. And it's always exactly this kind of question, okay, which is this. I'm going to write down the steps here, and then you have to provide what were the reasons used for each step, or what property was used. And so we're trying to say this A plus the bracket 3 plus negative A and bracket equals 3. So how do we simplify the left to get the 3? Well, the first step would be A plus negative A plus 3. What property did I just use? Okay. What did I do to go from here to here? I switched the order, which makes it commutative. Commutative for addition. And probably it'd be one of these technology enhanced ones where you're just dragging the property into the box. And they're probably going to have a commutative for multiplication as another option. So you got to have the addition. Okay, now what property would I use that lets me group A plus negative A? What did I just change? The grouping. The grouping would be associative. All right. A plus negative A is 0. What property did I just use? Say again? Somebody said it. Inverse, right? A plus negative A is 0. That's an inverse. But remember the identity, well, we'll get to the identity next. So that would be the inverse. Okay, now, and what property is it that tells us that 0 plus 3 equals 3? That's the identity. So that's the kind of problem. They're going to give you all these steps here and then ask you like to drag an item in here that's going to explain how did you go from here to here, here to here, here to here, here to here. And like I say, and we did terrible on that question last year. It was one of the most missed questions, but it was 1 out of 50. We still win. Our pass rate went from 65% 2 years ago to 85% last year. So, we're going to worry about one question when we know it's only going to be one? Probably not. Okay, that's section 1-2. Real numbers, properties of real numbers. Okay, this starts section 1-3. right? What is a variable? It's a symbol that represents a number. You know, generally it represents a number. A lot of times it's something we don't know, right? So there's some quantity we don't know. We represent it with a letter. What's the most common letter that we use? We use X. But you could also use, and you could use any letter, right? An expression is when you add a bunch of numbers or do a bunch of operations with numbers. That would be a numerical expression. We're more interested in algebraic expressions, right? Algebraic expressions have variables and numbers and operators all between them, right? That is an algebraic expression. Now, most of what we do in this class involves three different entities of math, right? One of them is an expression. An expression would be something like 2x plus 1. The next mathematical, I'm calling it an entity, would be an equation. An equation would be something like 0 equals 2x plus 1. So what turned that into an equation? The equal sign, right? The equal sign. And then the last thing that we deal with is called a function. And a function would be like y equals 2x plus 1. You know, there's too much laughing going on. And seats will change if I have to get quiet in here. Is that funny? Okay. And I'll call home, and I'm here every day, so detentions are nothing for me. I assign them weeks at a time. Okay. So what turned that into a function? Go ahead. What variable? The y, right? This one was 0 equals. Now we got y equals. I mean, what can you do with an equation? What do we usually say to do with an equation? You solve, right? You solve an equation. Okay. You can't really solve a function because it has two variables, one equation. I mean, you can solve it for y, but do you know the value of y? No. It depends what you plug in for x. What is the value of y? Right? So what you can do with a function is you can plug in a lot of values of x, generate a whole bunch of values of y, and then plot all those points. And then that would give you a graph. So we graph functions, we solve equations, and with expressions, we do two things. We evaluate and we simplify. And that's what we're going to do today, just a little bit of practice with evaluating and simplifying. Good? Is that? Are we done? Okay, look at this one. They want to know which one of these four is representing an algebraic expression 7 fewer than a number t. Which one of those represents 7 fewer than a number t? What does it mean, fewer? Less than, right? So is 7 minus t 7 fewer than t? Which one is 7 fewer than t? The c, right? So the answer is C. How about this one? Which one of these four is 2 times the sum of A and B? Okay? 2 times the sum. Well, where is the times in that H? The parentheses means multiply. What do we mean by the sum? It's the add, right? So the right answer is H. Okay, so when we evaluate an expression, What it means is you're going to get an expression and you're going to get a value of the variable and you're supposed to find the value of the expression for the given value of the variables. That generally turns into an exercise in can you do order of operations? And usually what do we use to remember the order of operations? The PEMDAS thing, right? So what do all those letters stand for besides, please excuse my dear Aunt Sally? Yeah. Parentheses, exponents, multiplication, division, addition, and subtraction. Okay, so when you have your expression, you're supposed to look at from left to right and then apply these rules, right? Now, the reason that multiplication and division are grouped is because you're supposed to kind of consider them like they're at the same level, from left to right. If you get to division first, you do the division, right? Because they're considered together. Same thing with addition and subtraction. Exponents. Exponents. Somebody, I think it was in our summer bridge, and some of you might have been in there, but somebody, they brought up this, no, it's none of you guys. It said, do you know that PEMDAS is wrong? And I said, no, I didn't heard that. He said, oh yeah, there's a video. You could go to YouTube and put in PEMDAS is wrong, and you'll get this video. So I did, and I went home and I brought up the video, and the guy definitely says PEMDAS is wrong. Now, if you listen to him, the guy says, well, it's not really wrong. It's just sometimes it's not taught correctly. It's not taught that the multiplication and division should be considered together, and the addition and subtraction should be considered together. So, you know, he's in one sense he's saying it's actually right, but maybe the teaching of it isn't always right. Ready? Okay, so let's try this one. The expression is 7 times a plus 4 plus 3b minus 8. Evaluate for a equals negative 4 and b equals 5. So try that now. What does this equal? Oops. What does that equal if a equals negative 4 and b is 5? See what you get. Do it. Wake up. Okay. Look like you were sleeping. Yeah. Who's got an answer? Curtis. Got a 7. 15. 7. You're getting outvoted. Any other answers here? What's that? Seven. The answer is 7. Right? That's actually not a difficult example of evaluating an expression. The next one you might find a little more difficult. When we're ready. Okay. Try that one. Yes. What'd you say? Come on now. Have courage. Now, what do you say? 20? No. No. Who's got an answer? 30? No. Who's got an answer? Who's got it? 18? 18 is correct. See, this is the kind of problem where we make a lot of mistakes. It usually happens when at least one of the variables is negative, and there's squaring going on, and there's minus signs involved. We usually make a fair amount of mistakes in that kind of simplification. That's why you want to be careful with this. 2 times, okay, x is 6, so this is 6 squared, minus, and y is negative 3. Okay, so what is negative 3 squared? It's positive 9. And if you put it in your calculator like negative 3 without parentheses squared, what is it telling you? It's telling you negative 9. It's wrong. You've got to know to use parentheses. And you know that squaring a negative number ought to be positive. Negative times negative is positive. So don't let the calculator, give you a wrong answer. You should know better than that. So this is, this is what a lot of times will happen, that in here, you'll see that minus and a minus and think that they cancel. But they don't, because order of operations says you would square the negative 3 before you'd ever try to do the subtract, right? And when you did the square of the negative 3, it's no longer negative, it's positive, right? So there's no cancellation of the minuses. So this is 2 times 36 minus 9 over 3, okay. Got to do parentheses, 2 times 27 over 3. Right, 27 over 3 is 9. So the answer is 18. Good. No, we're not doing that. Sorry. Okay, next, simplifying expressions. First, there's a couple of vocabulary words that we have to be familiar with because we're going to use them over and over again. One of them is term. What do we mean about a term in an expression? And the easiest way to kind of get at it is just say, in this expression right here, how many terms do you see? 4ax, negative 4ax plus 7w minus 6. How many terms is that? It's 3. How do you identify the terms? How do you distinguish between them? They are separated by pluses or minuses. So this is 3 terms because it's got 1 plus and 1 minus. So 1, 2, 3, 3 terms. So that's one thing. Got to know what we mean by a term. Second, if there's a constant in front of the variable, that is called coefficient. Okay, and we'll use that word over and over again. We're not trying to confuse you. That's the proper word to use, coefficient. And finally, when you have a term that does not have a variable in it, that's called constant term. Right? So this minus 6 doesn't change based on the variable, so it's constant. It doesn't change. So those are 3 good vocabulary words: term, coefficient, and a constant term, or just a constant. You done? Natalie? Okay, so here we've got, we're into the phase of simplifying expressions. And basically you simplify by combining like terms. So what do we mean by like terms? Right, as it says right here, like terms have the same variables raised to the same powers. So for example, 3x squared and 5x squared, they both have x squared. So you can combine them. How do you combine them? You combine the, what's the vocabulary word from the last slide? The coefficients, right? You add or subtract the coefficients. In this case, it is 3 plus 5 x squared, right? You combine like that. And it does not change the squared. Don't try to turn that into a fourth, right? It's not x to the fourth. Think of it like, 3x squared plus 5x squared. It's like 3 oranges plus 5 oranges is 8 oranges, right? It doesn't change the oranges. And it doesn't change the x squared. It's still x squared. Okay, now notice these two in red. Y to the third z. They've got more than one variable, but they're all raised to the same power. So they're like terms. So how are we going to combine 9y to the third z and negative 4y to the third z? How many y to the third z's do we have? You have 9 minus 4 of them, right? 9 minus 4. So that is. And then what about the 2yz? Will we be able to put that with any of the other terms? No, because there's no other term that has exactly y to the first, z to the first. We just have to say that's 2yz. Okay, 3 plus 5 is 8x squared plus 5y to the third z plus 2yz. Right, that's simplifying. Most of our simplifying is just combining like terms. Okay, what combine like terms there? What do we get? Curtis? No. Oh, Shiza. She's that. Okay. 3x squared plus 5y squared. So notice the like terms are here and here and here and here. So, they're showing a lot of, using the properties. They switched the order in order to get the x squareds together. Do they really have to do that? No. But in the end, they did that. Eventually, they get to the 7 minus 4 times x squared, 3 plus 2 times y squared. Good? What's that? Okay. Okay, how about this one? What will we have to do on this one in order to simplify? You're going to have to distribute, right? How many times you got to distribute here? Twice, right? You got 2 times the distributive property. What are you distributing here? The negative, right? What's that going to make these terms when you distribute a negative? It's going to make that negative 3k and minus m. Okay, and then the 2 times k and 2 times negative 4m. Then combine the like terms. It looks like when it comes to the k's, you got negative 3 plus 2 times k, which is negative 1. Where's the 1? You don't have to write the 1. Especially in like this level of class, we shouldn't be writing the 1. Just write negative k. And then the m's are negative 1m minus 8m. Right? You don't see a 1 there, but there's a 1 there. Negative 1 minus 8 is negative 9. And although I have another slide here, I think I'm going to just leave it at that, okay? I'll give you the homework because you'll end up doing these anyways instead of having you do this extra. So this is what we did today, right? We did the properties. We did with real numbers, and we did the properties. But we know how that will apply later when we get to complex numbers. And we reviewed simplifying expressions, combining like terms, and evaluating expressions, substituting for the variables. Right? That's the homework.